Today our lesson is about blue. Bluey. Let's see if it'll let me sign in. There we go. The features of functions. It's going to be a good one. It's going to be, actually, this is not as bad as what you guys think. This is a lot of looking at graphs and saying what's happening. So right now, when we look at this graph, how can we talk about it? What things do we notice about it? What are the important things? We can describe its x-intercepts, right? We have x-intercepts. We have a y-intercept. And how else can we describe it currently? In our what our language might we have? You can make an XY chart, right? And give points. That's all we have right now to talk about graph. Now, if you're in the business world, points are nice and intercepts are fine, but you want to know, like, am I increasing or decreasing, right? Is the revenue increasing or decreasing? That's actually all of calculus, if you go on to it, is all about describing what's happening to your graph. That's pretty much, this is a very good intro to the future. We just talked about it. That's what we talked about. X-intercepts, Y-intercepts. Naming a few points. So I gave you a really, we just went through 5 slides pretty quick, so nice job, team. This is the technical definition for increasing, decreasing. I'll never anticipate or expect you to have this memorized or know it. All it's saying is if something is increasing, if B is bigger than A, then F of B is bigger than A. If it's increasing, the bigger my X, what should happen to my Y? It goes up. And decreasing is the opposite. If B is bigger than A, then it should go down. Okay? Again, not going to make you memorize it. If you want to go through more theoretical, you can watch the other video posted. This is going to come up. If you move onward in math, you'll see this a lot. And you will have to know it a little bit more. Here's the layman's term version of it. Increasing means the Y value increases. My money over time is going up. Decreasing is going down. Like if you bought Bitcoin 4 weeks ago. Constant means it's flatlining. It's not going up nor down. It's staying the same. What might be an example of a constant in real life?
That's R versus freshman year.
Okay. What about if you set your cruise control on your vehicle at like 60? Is that a constant? Like if you were to graph the speed over time, it'd be a straight line. Okay. I should randomly mic up one student in the room each day. And it'll never be a certain person. All right. So let's talk about now this graph. We're adding a new vocab to how we can describe it. Intervals from -2 to -1. So from -2, somewhere up here, to -1. So I'm going from there to there. What is happening to my graph? Is it going up or down or staying the same? And when you read this, read it like a book, right? We always go left to right. So it is going down. It is decreasing. I don't know why that's a cursive G. Does that make sense? You just look at it. Went down. What about -1 to 1.5? Okay. what is going on from here, to here on this graph? Is it staying the same? No. Is it doing multiple things? What's it doing first? It decreases. Then what does it do? Increases. You go down, and then you go up. Erase this. What about 1 to 2? So from 1 to 2, I am increasing. 0.5 to 2.5. This is our decrease and increase. I'm not going to talk about too much. But how do you guys feel about that? Are you okay on that? If I gave you an interval on a graph, could you tell me is it going up or down? Again, very few constants. You're just going to look for that flat line. Do you guys want to go over this one, or do you feel okay about it? All right. Again, if you would like to see that example, it is posted. There is a way to see that example as well. This is kind of the Cliff Notes version of a longer spiel. All right. This one I like because it's asking a little bit different. It's asking where is the function increasing, where is it decreasing, and where is it constant? Okay. So we're going to do this. Should I do it the calculator or the college algebra way? Let's do the college algebra, and then I might have to fix it later. I'm going to see how I input it. So where am I increasing? I'll start with the first one. Where am I increasing? Okay. So I'm going down, then I'm coming up, and then I'm going back down, right? I know it's hard to see. These are negative 1.58, we'll call it, comma negative 0.38. That's that point, and this point is negative 4.2 and 0.38. So that's what those points are. So where am I increasing on this graph? Right here, right? So I'm increasing. Use our x values. It's where. Where is always x, right? So where am I increasing? I'm using my x values. The y's don't mean anything. I'm asking it where. Where am I increasing? I'm increasing from negative 1.58 to negative 0.42. I am using parentheses on this when I label it, and here's why I'm using parentheses. At this point, at this exact point, am I increasing or decreasing? That's where I change direction, right? So I'm neither. That's actually a constant, okay? So I use parentheses when I do increasing and decreasing intervals, okay? I'm going to teach you guys how we do it. So where am I decreasing? Well, how far does this graph go to the left? Forever, right? This domain is all reals. So I'm decreasing from negative infinity. This is where interval notation really wins because I'm just listing my x's as between. So over here is negative infinity until I hit that negative 1.58. That's where I'm decreasing. And I'm also decreasing from this point to the right, right? Maybe. Where am I constant? All right. So this isn't going to come up a lot in this class, but I will talk about the constants are at x equals negative 1.58 and x equals negative 0.42 because that's where it changes direction. You cannot be increasing or decreasing at those points. Those are actually called inflection points or critical points, inflection points. Not inflection points, critical points. Yeah. In calc, you use those points to figure out when your like revenue is going to change from increasing to decreasing or decreasing to increasing, or when something changes direction. Or that's pretty much all you do in calc is find those points. Where do you change direction? Yeah. So make sure that you can read a graph and tell me if it's increasing, decreasing, and then put the points on and give me the intervals where it's going up, going down. Again, why did I use an interval for constants? Is because it's only at one point. There's not, once I go microscopically to the right, it's decreasing. Okay? There's not a whole lot with that. What? Say it again. What do you mean? Like if you go right to the right? Yes. For the constant, like if you go right to the right, if it's a straight line, though, it's going to be constant no matter, like it won't be increasing or decreasing. So if it's a flat line, then yeah, if I go right to the right, it'll still be constant. But you won't see that very often because not many functions have a flat line. That'd just be like y equals something, which you don't even, I guess you would, right, f of x. All right, local extrema. Ugh. Ugh. What this says is something is a max if it goes up and then comes down. This point would be a max, a local max. And this says if something goes down and then comes up, that's a min. Okay, that's the putting it in as best terms as I can. You do not have to use that definition in here to figure these out. You can figure it out by looking at the graph. A valley is a min and a hill is a max. Yep, they're saying the same thing. And that is an absolute. So what's the difference between, I don't know how you jot this down. This is a local min because it acts like a minimum. It goes down, then comes up. But are there values smaller than that on this graph? Yeah, it goes to infinity, right? This is an absolute min, absolutely, because is there any value below that on this graph? No. This is also by definition, it's also a local min because anytime I go down and then come up, it's a min. It's a local min. Now it's an absolute if there's nothing else below it. That's what it's saying. Same thing is true with this one, right? That's a local max. This is a absolute. Because I can't go above it. I drew those on the wrong ones, I do realize. My apologies. I wasn't reading it. So in further math classes, it would be your job to find those mathematically. In this class, we're going to find them graphing. We're just going to look at the graphs. I know this sounds wild, but honestly, the difference between calc and algebra is nothing. Calc is algebra. It's just like algebra 3. Calc 1 at least. All right, so find the local absolute extrema for this function. How many times is there curves in this? There's only one, right? So when I look at this graph, there's only one. I know I'm using these. Right? There's only one. Do I have any maxes on this piece? Is there any points at the top of a hill? There are no maxes. Do I have a local min? Is there a point that I go from down to up? Yeah, right there. You'll have to take my word for it because your graph is hard to see. We have a local min, and it's going to be at 0.5, negative 2.25. I don't know if you guys can see that. This is where the min occurs. The y value gives you the value. So if they're asking what is the value of the min, it's the y. So remember, when I talk about this a lot, where is your x? What it is your y. Like, what's the value of it? So your local min occurs at this point. The value of it because you'd want to know, like, where's my least amount of money I'm going to make and what is it? Okay? So that's my point. It'll be really clear. It'll ask you, what's the y value of the min? Or it'll say, hey, what's the point of it? Now, what's crazy about this one is, are there any points below this? No, so this is also your absolute. They're the same value. They're the same exact thing. Depending on the book. A lot of them that we did, you would just write the absolute min as this because then it's assumed it's also the local. Yeah. No, you'll see when you do your homeworks and stuff, you just have to know absolute. You'll be all set. Oh, that's a good question. All right. Guys. All right, let's look at this one. This is the same graph we had before with these wild negative 1.58, negative 0.38. We need these points. They're really going to be important to us. I don't know why they're so important. All right. So now in this graph, local absolute extrema. So let's talk about our local max first. Do I have any local maxes on this? Points that I go up and then I go down. Right here. Anytime I'm at the top of a hill, it's a max. So that's my local max. The value of it's 0.38. Now, are there any points on that graph that are above this beast? Yeah, so it's not an absolute, right? No absolute max. You don't have to write there's no absolute max, but if you want to remind yourself, there is not one. Just local on this one. It acts like a max. It thinks it's the max. It's walking around, strutting around like it's some sort of big dog, but really this is the big dog over here. Okay, we all know that max that's walking around wearing a boot. I'm sorry. All right. Local min. Now, is there a spot that acts like a min? This one goes down, comes up. This one acts like a min, but there's definitely ones that are worse. Because over here, we actually go to negative infinity. It has end behavior. So that's our local min. We do not have an absolute min. Okay? Pretty much those two graphs for this class will represent every graph you'll see with like increasing, decreasing, local. You know what I mean? Because we're not going to get too tricky yet. Questions on that? So you need to look at the graph. What if you're given a function and they don't give you a graph? What should you do with that function? Graph it. You guys don't have the tools yet. So like, I'm not going to go through this one because it's a lot. If you want to watch it, you can. But first thing I ever do, or even I teach when I taught AP pre-calc or I taught calc, the first thing you do with any function that you cannot see, you graph it. So what's the first thing I'm going to do with that function if I want to look at the behavior? Graph it. Because once I have the graph, I just use that to determine the behavior. I'm pretty confident when I looked at the test, it is made in a way that you do not need, it draws the graphs for you, so you never have to graph on it. Does that make sense? All right, we are actually really close done. Something else we need to talk about is called the average rate of change. Average rate of change. Where have we heard that term before? Slope. We're going to be finding slope again. All right. We call it arc. Average rate of change. Okay. Maybe it's, never mind. I don't know if I can make that joke. All right. So, given 2 points, the average rate of change is equal to that. That's our slope formula. That's it. Oh, I hate that. Yes, mine. I'm not gonna do this example because it takes so long to plug it in. Sound good? I'll do this example. Does that sound good? All right. So let's find the average rate change of h of x is equal to that. So that looks like a parabola, right? It's going to be an upside down parabola. Actually, I am going to graph it because I want to show you guys. Let's do this. Oh, I was looking at my multiplication charts earlier. What? I need help, man. It's my first time doing math. What was that function? Was it negative x squared plus 5x? Then I'm sorry, what's the last part? 2? So that's what my graph looks like, right? My sketch was pretty close. Not bad for a government employee. All right. So we want to find the average rate change, the arc. And my first interval was from what to what? 0 to 4, right? So this is in your notes on that. I'm just going around. So here's what I'm going to do. At 0, I'm here. And at 4, I'm right here. So I'm finding the slope of that line between those 2 points. And the reason why average rate of change is important because if this is actually arc is important. If you ever stock trade, buy stocks, stocks don't go like this, right? They go like this. You know what I mean? So what you do is you actually find the average rate of change on those stocks to tell you what's the general feel of it. Is it actually going up or down? Because in a given day it might go down, or in a week it might go down. But what's the 3-month average moving yield is what you look at. So this is something, if you buy stocks, this is actually the best indicator for long-term success of it still. No, because that's not how it works. Oh, kind of actually. They do look at trends. So arc of this function, I need 2 points. If I have 2, If I have 2 points, I can find the slope. Do I have my x values to find my slope already? Yeah, this is my x1, x2, right? How am I going to get my y values for it? I plug in my x. So f of 0 is 2, right? So that tells me the point 0, 2 is on the graph. When I plugged in 0, I got 2, right? Because if I gave you guys 2 points, y'all can find slope. Done that. If I do f of 4, yipers, negative 4 squared plus 4 plus 5 plus 2. I wrote that down somewhere because I didn't feel like doing it. I got 6, right? Got 6. So I have the point 46. Okay? And that makes sense when I look at the graph. Those are the points I graphed as well. But that's how I get these 2 points. And now from here, I have an x1, y1, and an x2, y2. So I do slope formula. X minus x, y minus y, 4 over 4, 1. So what's the slope of the line between those 2 points? 1. The only difference from this and what we did in Unit 1 is, or Chapter 1, was we have to plug in my x's to get my y's. I have to plug those in to get them. All right. Does that match what I see on the graph? It does. All right, let's do another one of these because they're good for us. And then I'll show you a trick, one that you don't have to do any math for. All perfect timing. Not perfect timing. All right. What about from -2 to 3? So -2 is down here, and 3 is right here. What kind of slope should I expect on this one? Pretty big, right? That's gonna be that should be a higher slope. So I need 2 points. I need an x1, y1, right? So how do I find my y to my -2? What do I do with it? Plug it in. I did not do this one ahead of time, so I apologize. I'll have to do the math. Oh, I can cheat. Watch this. X equals 2. I can't see that. That's cool. And where do they cross? -12. So when I plug this in, I get -12. So that's my y value. Right? So that's my 1 point. And how do I find my other y point? Well, I plug in the number. I'm going to cheat again because you're allowed to cheat at this and your taxes. Don't cheat your taxes, kids. I was just kidding. No, you can't. Well, I'm just doing that to save time. I would have plugged it in. Yeah, in 3/8. All right. Now what do I do with these 2 points? Find the slope. So that becomes positive and positive. Ask me if I'm sure. I'll say I'm positive. Slope is 4. Does that make sense? Is that a pretty large positive slope? Yeah. The next slide I'm going to require 0 works. Guys, what's the... Look at this one for a second. Could I go through and plug it in and find points and then do whatever? Yeah. What does this graph look like? It's in slope intercept form, so what shape is it? It's a line, right? So I have a slope. So what's going to be my rate of change between any 2 points if it's a straight line? It's all going to be a half, because that's my slope. If I take 2 points on it and find the slope, I should probably get the slope. All right. All right. We're almost there. Where's the next packet? All right. This next one is going to be very new to y'all, but don't overthink it. What if we have functions inside of functions with functions on top? This is 3, 4. I think I labeled them. This is going to be wild, guys. Hold on to your hats. New notation. If it says to add my two functions, what do I do with my functions? Add them. If it says f minus g of x, I do f of x minus g of x. If I do f times g of x is equal to f times g of x, which is equal to f of x times g of x. And if I do f divided by g of x is the same as f divided by g of x, which is equal to f of x divided by g of x. Don't overthink this lesson, okay? I've taught this for many years. People overthink it. This looks crazy. But do what it tells you to do. If it tells you subtract, subtract. If it tells you to add, you add. For example, let's do one. This is my f of x. This is my g of x. Two different functions. F plus g of x is the same thing of f of x plus g of x. Right? So what do I do with these two functions? You add them. Yeah. I do 3x minus 4 plus x squared minus 1. Okay. Now, that's an okay answer. You guys remember back in the day, write it in order of highest power to lowest power. First, second, negative 4 minus 1 is negative 5. There we go. We did it. Oh, I'm out. All right. If it says subtract, what should we do with our functions? You subtract them. Now be careful on this one because I do have to treat this kind of like parentheses, right? Because that negative has to go through. Even this one, you could think about it as keep them separate until you do the operation, right? Because I need to change both my signs. So that becomes a negative x squared and a positive 1, right? Negative x squared plus 3x. Now we have a negative and a positive. Okay. I don't want to do this. All right. So what do I do if I multiply my functions? I'm going to come over here for this one because I'm running out of room. I would do f of x times g of x, right? So my f of x is 3x minus 4. My g of x is x squared minus 1. We do have to simplify this one. Okay? What's up? All right. But I do need to FOIL this beast. 3x times x squared is 3x to the third, right? First, outside. Oh, yep. Negative 4 times x squared. And negative 4 times negative 1. Ah. Bless you. Okay. If we're dividing, what do we do? Divide. F of x is 3x minus 4. G of x is x squared minus 1. Done. Done. That one's done. No, absolutely not. Uh-oh. Watch this. What changed between these two slides? Oh no. Mamma mia. What do we do with that 3? You just plug it in. So if it's f plus g of 3, I take that 3 and I plug it in for x. I didn't do it. So what's that? 9 plus 9 is 18, 13, right? Any questions what you do here now? So you plug in that for your x. Is there another way you could do this if there's a number involved? Yeah. Let's say I did not want to FOIL because it's too much work for an old man like me. I'll do this one though first. Our subtraction, I plugged in 3, negative 9, 9. I got negative 3 as an answer. All right, now time for the old man work. What if I don't want to FOIL it? So I told you it's f. This is the same thing as f of 3 times times g of 3. Can't I just plug into 3 to both and get a number and then multiply them? Yes, it works either way. Both ways work every single time. Some ways it's easier to do this and then plug it in. Some ways it's easier to plug it into each function and then figure it out. Because 3 times, because now I don't have to FOIL. I don't want to FOIL. Right? 9 minus 4 is 5 times 8. So that's a lot easier than having to find x, right? I just plugged it into each individual function. Actually, could I have just done this to start with and done, what's 3 times 3 minus 4 is 5, right? F of 3 is 5. So wherever I see the f of x, I just plug in a 5, right? And here I could have done g of 3. 3 squared minus 1 is 8. So I just did 5 times 8. Or down here, what's my f of 3? 5 over my g of 3 is 8. So I could have plugged it into the functions my first step, like plug 3 into both of them, or whatever they want it to be, and then just done the multiplication, addition, subtraction, or division. Okay? All perfect. All right. Yeah, you can watch those on your own time. There we go. So what's a composite of a function? A composite of a function is a function inside a function. It's functionception. Fog. Goff was in a fog yesterday. All right. If I see this dot, it means f of g of x. It tells me I'm going to plug my x into g and take that output and plug it into f. This looks scarier than what it's going to actually be when we do examples, okay? It looks scarier than what it is. It's just saying f of g of x. This is saying f of g of x. All right, let's try one. This one has a square in it. They both. I don't want to do it that way. We'll be okay. This is my f of x and g of x, same ones from before. So I'm doing f of g of x. Okay. If I say that's f of 2, anywhere I see an x, I plug in a 2, right? For this one, anywhere I see an x, what do I plug in? The other function. The other function. So what this is telling me is f of x is 3 times something minus 4, right? That's what f of x is. what do I put inside of that parentheses? The g of x. Okay. I'm going to distribute that through because it'll look better. So I get 3x squared minus 3 minus 4. Okay. So that's f of g of x. I plugged a function inside of a function. This one, though, is g of f of x. So I go from inside to outside, but I'm going to start with my outside. G of x says something squared minus 1, right? Whatever's inside that, I put in here. It could be anything. What do I plug inside there? F of x. I'm not, so you could distribute that out and FOIL it out. But that will work. That will actually work. That's a function inside of a function, right? Are these the same thing? Are they going to be the same thing? No, they are not. F of g of x and g of f of x are not the same thing. It is not commutative. Oops. Yeah, it does not work. And you can test that out by plugging in 5, I think. I actually might be able to do this. Again, if you want to see this, what would I do if it's f of g of 5? What do I do with it? Actually, I will show you this. I can show you the graphs tomorrow. It does not take long. All right, so we all agree that, well, I agree. If we have that number, I can just plug it into that function we just found, right? And it'll work. But let's say I have to do this and I don't want to do that. So this is f of g of 5. So what I could do, if I don't want to do algebra, I just want to do base, like arithmetic, I could do g of 5 equals 5 squared minus 1, right? Which is 24. So this is the same thing of f of 24. Why can I say that? Because what's g of 5? 24. So then I take my 24 and I plug it into that. If you don't like this way, you can just do the other way. 72, 68. So you guys see what? So I plugged it into this function first, got my output, and then plugged into that one. Okay? Yes, that's how I got the 24. So I could do it in the other way too. G of f of 5. What's f of 5? What's that? 11, right? So then I do g of 11, right? So I'm plugging it in to get the output, plug into my function. So that's 11 squared minus 1, which is 120. Okay? So big thing is, this is not commutative. They're not the same. If they are the same, that's something really special. That's called an inverse. All right? We will do, that's just proving there. We will do the graphs tomorrow. It'll take probably 5-10 minutes.